Bismillahirrahmanirrahim. Nous sommes réunis aujourd'hui pour examiner le travail de thèse point de vue d'obtention de doctorat en chimie spécialité chimie physique, donc présenté par Ben Mabrouk Marwa, intitulé Synthesis, Characterization and In Silico Exploration of an Salicylic Aniline Shift Base Derivative DFT Antioxidant Activity and Molecular Docking Studies. Donc vous avez 30 à 40 minutes pour exposer l'essentiel de votre travail.
Bismillahirrahmanirrahim. I would like to begin by expressing my sincere gratitude to the members of the jury for accepting to evaluate this work. I also would like to express my special appreciations for my advisors, Dr. Siridi and Dr. Aimi. You have been tremendous mentors. Thank you everyone for attending. The title of my thesis is Synthesis, Characterization and In Silico Exploration of N-salicylidene aniline shift-based derivatives, DFT, antioxidant activity and molecular docking studies. To give you an idea of how I'll be presenting my work today, here's a quick outline of the sections we'll be covering. First, we'll start with an introduction to the subject. Then we'll delve into shift bases to have a good understanding of what they are. Next, we'll discuss free radicals and antioxidants. Then we will explore computational methods that we have been using during this research. The main part of these presentations focus on the results and the discussion of my findings. Finally, we'll wrap up with concluding remark and future perspectives. Let's start by presenting the context of this research. Oxidative stress contributes to the development of various diseases like cancer, neurodegeneration, and heart problems. Research has shown that antioxidants are effective in combating free radicals and reducing their harmful effects. However, current therapeutic options often face limitations such as low potency and dangerous side effects. This ongoing need for better antioxidants motivates the exploration of new therapeutic options. Research also have shown that shift bases with their adaptable chemical structures and diverse biological activities offer a promising novel therapeutics. However, a comprehensive understanding of salicylidene aniline shift base derived from meta-substituted aniline and their antioxidant properties remains limited. Our research addresses this gap by investigating these derivatives and their potential to combat free radicals. We specifically aim to identify their structural characteristic, explore their antioxidant activity, and assess their potential as therapeutic leads. Before we explore our salicylidene aniline derivatives, let's build the foundation by understanding shift bases themselves. Hugo Schiff recorded the first synthesis of shift bases in the 19th century. Shift bases are considered molecule bearing an imine group. It is usually formed through the condensation reaction between a primary amine and an aldehyde or a ketone. In this reaction, the lone pair of electrons on the amine acts as a nucleophile attacking the electrophilic carbonyl carbon of the aldehyde or ketone. This leads to the formation of a new carbon-nitrogen bond and the elimination of a water molecule. Shift bases are an important group of organic compounds having a vast range of applicability in various fields such as inorganic, biological, and analytical chemistry. There are large implications in biological systems as antioxidant, anti-inflammatory, antimicrobial, anti-cancer, etc. have them highly important for medicinal and pharmaceutical industry. Now let's shift our attention to oxidative stress and antioxidants. Free radicals, also known as reactive oxygen species or reactive nitrogen species, are unstable molecules with unpaired electrons, which makes them ready to steal electrons from other molecules, causing oxidative stress that can harm vital biomolecules like lipids, proteins, and DNA. These free radicals can be generated naturally during the metabolism process or through environmental factors like radiation or cigarette smoke. The danger of these radicals lies in their ability to trigger chain reactions. The process begins with the initiation stage where an external factor or internal process generates free radicals. The highly reactive molecules then attacks a nearby stable molecule in the propagation stage, stealing an electron and generating another free radical in the process. This new radical goes on to attack another stable molecule, continuing the chain reaction. The cycle is only broken in the termination stage when two free radicals react with each other or when antioxidants intervene. So what are antioxidants? Antioxidants are a diverse group of molecules that protect our cells and biological systems from the damaging effects of free radicals and other reactive species. Antioxidants can be classified based on their sources into endogenous antioxidants and exogenous antioxidants. The endogenous antioxidants can be enzymatic like superoxide dismutase and glutathione peroxidase. They can also be non-enzymatic like glutathione and uric acid. On the other hand, exogenous antioxidants can be natural like vitamins A, E, and C and phenolic compounds. They can also be synthetic like butylated hydroxyl anisole and propylgalate. In this work, we explored three shift-based derivatives following these steps. First, we synthesized these compounds, then used different spectroscopic techniques to characterize them. We then investigated their electronic properties, providing insight into their reactivity. We assessed their ability to scavenge free radicals through various mechanisms. To gain further insight into their potential bioactivity, we performed molecular docking simulation and assessed their ADME properties. During this process, we heavily relied on molecular modeling because of its low cost and high accuracy. Here's the method that we used. For DFT calculation, we used Gaussian 9 software with B3 functional and 6311 plus GDP basis set. We included IEF PCM solvent model to consider the solvent influence. We used TDDFT with CAM B3 functional and 6311 plus GDP basis set for UV visible calculations. For the docking protocol, in the preparation stage, we used AutoDock4 to prepare target protein. This involved removing unnecessary molecules and adding polar hydrogens and calculating Coulomb charges. For the docking simulation, we used the AutoDock4 with Lamarckian genetic algorithm for docking simulations. In the visualization process, we used docking discovery 4. For the ADME assessment, we used PKCSM web server to predict ADME properties, which refers for absorption, distribution, metabolism, exertion, and toxicity of the compound. We used Swiss ADME platform to evaluate the drug likeness of the compounds. Now moving to the most important part of this presentation, which is the results and discussion. 3 shift bases were synthesized. First one, beryllium chloro group, which will be referred to later as HBMC. Next, the second one is beryllium anode group and nitro group, which we'll refer to as HBMN. And the third one is beryllium methoxy group, which we will refer to later as HBMM. For this reaction, equimolar quantities have been we added equimolar quantities of salicylic aldehyde and primary amine in minimum quantity of solvents. The mixture was refluxed for 2 hours in 60 degrees Celsius for 2 hours. The product obtained was filtered, then washed with ethanol. Following the successful synthesis of the targeted shift-based compounds, various spectroscopic techniques were employed to confirm their structures, starting with proton NMR. The analysis of the proton NMR spectra revealed key structural features. A characteristic singlet signal within the range of 13.2 to 12.5 ppm was consistently observed, indicating the presence of phenolic proton. Furthermore, the formation of stalicidin aniline was supported by distinct singlet signal at 8.7 ppm corresponding to the azomethine protons. Multiplet signals in the range of 8.1 to 6.8 ppm were attributed to the aromatic protons. HBMM displayed a unique singlet signal at approximately 3.8 ppm, consistent with the presence of its methoxy group. Analysis of the experimental infrared spectra revealed that all three derivatives exhibited OH stretches around 3,440 reciprocal centimeters, indicative of the phenolic hydroxyl group. The stretching vibration of the imine bound appeared in the range of 6019 to 6023. The aromatic CC stretching vibrations were observed within the expected regions of 1650 to 1200 reciprocal centimeter for all compounds. Furthermore, the spectra displayed distinct peaks corresponding to the specific substituent group present in HBMC CCl. Stretching vibrations was identified at 687 stretching vibrations, and which is consistent with the expected range for such bound. For HBMM, the presence of the neutral group was evident from two characteristic absorption bands: the asymmetric NO2 stretch at 1523 and the symmetric NO2 stretch at 1352. For HBMM, the ether bound appears at 1040. These experimentally observed vibrations frequencies closely match the values predicted by computational methods, supporting the proposed structures of the shift-based derivatives. The influence of solvent polarity on the spectroscopic properties of the investigated compounds was explored using UV visible spectroscopy. Spectra were recorded in three solvents with varying polarities: ethanol, chloroform, and benzene. Gratifyingly, all compounds displayed two distinct absorption bands regardless of the solvent used. The first band positioned in within 262 to 269 nanometers range is characteristic of the p star electronic transitions. The second band, observed in the range of 331 to 337 nanometers across the three solvents, is attributed to the n-p star transition. These transitions are consistent with the presence of the azomethine group and aromatic rings. The spectra consistently show absorption band below 400 nanometers, which indicates the dominance of the enol tautomer. These findings align well with the theoretic calculations. Global reactivity descriptors were calculated in gas phase to probe the stability and potential antioxidant properties of the studied shift bases. In these results, HBMM have the highest HOMO energy and the lowest electronegativity, which suggests enhanced electron donating ability. HBMN have a lower REMO energy, implies a stronger electron accepting capability, both of which are beneficial for antioxidant activity. Smaller energy gaps generally indicate greater reactivity and reduced stability. Consistently, the molecules' chemical stability and the order can be ordered as follows: HBMM, then HBNC, then HBMN. Compound HBMM appears to be somewhat more promising target for electron scavenging process. Molecular electrostatic potential maps were generated to visualize electron density distribution and predict reactive sites within studied compounds. In these maps, high electron density regions are shown in red, while low electron density regions are shown in blue. Our map reveals concentrated negative potential around the oxygen atom with a minimum between -29 to -24 kilocalories per mole. Conversely, the most positive potential regions surround the phenolic hydroxyl hydrogen atom. These findings suggest that electron and hydrogen atom donation to oxidizing species is most likely to occur at these positively charged sites. Now, the antioxidant mechanisms. Previous studies suggest that the presence of phenolic hydroxyl group in phenolic compounds is responsible for their capability to scavenge free radicals. And it takes effects mainly through three mechanisms: direct hydrogen atom transfer, stepwise electron transfer, proton transfer, and sequential proton loss electron transfer. To gain deeper insight into these antioxidant mechanisms, we employ density functional theory calculations. This approach allows the quantification of key thermodynamic parameters like bond dissociation enthalpy, ionization potential, proton dissociation enthalpy, proton affinity, and electron transfer enthalpy, associated with different radical scavenging pathways. Calculated enthalpies of our compounds along with the established antioxidant Trolox as a reference provide the basis of our analysis. First, let's take a look at the hydrogen atom transfer mechanism. In this mechanism, the phenolic hydroxyl group donates a hydrogen atom to a radical species, forming a less reactive phenoxyl radical. The ease of hydrogen atom transfer is determined by the bond dissociation enthalpy of the OH bond. As we can see in this chart, HBMC consistently has the lowest BDE across various environments. This suggests it's the best hydrogen donor among the three, followed by HBMN and HBMM. Interestingly, all their BDEs are comparable to Trolox, hinting a promising antioxidant activity. An interesting observation in the increasing BDE with solvent polarity, this tells us that the ease of hydrogen donation decreases slightly in solvent compared to the gas phase. Now, single electron transfer, proton transfer mechanism. In this mechanism, the antioxidant first donates an electron followed by a proton. Lower IP and PDE values favor this pathway. HBMM have been shown to exhibit the lowest IP in all environments, indicating the strongest electron donating ability. However, the IP trends differ from BDE, likely because IP reflects the entire molecules, while BDE is more sensitive to the local substituent effects. Although the IPs for our compounds are higher than Trolox, they still suggest potential antioxidant activity through this mechanism. The choice of solvent significantly impacts IP. We see a consistent decrease in IP from the gas phase to more polar solvents like water. This highlights the influence of solvent polarity on stabilizing the radical cation intermediate. Finally, the sequential proton loss electron transfer. Here, the antioxidant first loses a proton followed by an electron transfer. Lower PA and ETE values favor this pathway. Our analysis shows that HBMN consistently exhibits the lowest PA across all environments, signifying its strongest potential for deprotonation. PA values decrease significantly from the gas phase to solvents. In conclusion, the dominant antioxidant mechanism seems to depend on the environment. In the gas phase, HAT is the most favorable pathway due to the relatively lower BDE values compared to the IP and PA. However, in polar solvents, split gains prominence due to the decreased PA and ETEs. The sum of enthalpies associated with the split action, PA plus ETE, is minimal for HBMC, which suggests that it has better tendencies for radical inactivation. Now let's shift our focus to the predicted bioactivity and potential binding interactions of our shift-based derivatives. First, we employed PASS, which is an online program adapted to evaluate the overall bioactivity profile of organic drug-like molecules by analyzing their structural features. PASS can predict a wide range of biological activity simultaneously. The analysis of the compounds using PASS program revealed that all three compounds have a high potential to inhibit an enzyme called ubiquinol cytochrome C reductase binding protein. This prediction is supported by the high PA values, which range from 0.8 to 0.9. Let's take a moment to understand the significance of this protein. This protein is a subunit of the complex 3 of mitochondrial respiratory chain. It plays a crucial role in energy production. However, this protein also generates reactive oxygen species which can damage cells if not adequately managed. Interestingly, research suggests that carefully lowering this protein activity might be beneficial for some cases, like hindering tumor growth by reducing the formation of new blood vessels. This is why the predicted inhibition of this protein offers a multi-pronged therapeutic strategy. First, reducing reactive oxygen species production and potentially combating diseases where this protein is overactive. To further explore this potential, we conducted molecular docking simulations. Molecular docking is a computational tool used in drug design to predict how potential drug molecules interact with their target proteins. In our case, we used it to assess the inhibitory potential of HBMC, HBMN, and HBMM against the ubiquinol cytochrome C reductase binding protein. The docking results were encouraging. HBMM displayed the most favorable binding energy, clocking at 7.6 kilocalories per mole. These binding affinities are comparable to similar molecular systems reported in previous studies, which adds credibility to our findings. Calculated inhibition constants further supports these results. Now let's take a closer look at the specific interactions governing how these compounds could bind with the protein active site. Conventional hydrogen bonds play a critical role in anchoring all three compounds. The phenolic hydroxyl group consistently form a strong hydrogen bond with aspartic acid and serine. Interestingly, the nitro group presents only in HBMN, establishes additional hydrogen bonds with lysine. Beyond hydrogen bond, the aromatic ring is in our compounds contribute to overall binding stability through various hydrophobic interactions. These include PP stacking and P-alkyl interactions. The methoxy group in HBMM also participates in these hydrophobic interactions. The chlorine atom in HBMC might add a layer of binding specifically through alkyl interactions. This intricate network of interactions underscores the potential of our shift-based derivatives to bind favorably within the ubiquinol cytochrome C reductase binding active site. Now we explore the potential of our shift-based derivatives as drugs by examining their ADME properties, which refer to adsorption, distribution, metabolism, and excretion. The calculations show a good oral absorption, limited central nervous system penetration, potential drug-drug interaction during development, and suitable duration of action and promising toxicity profile. Building on the encouraging ADME profile, let's now explore into the physicochemical properties of our compounds. These properties influence a drug's behavior in the body. The results are encouraging. All three compounds comply with the Lipinski's rule of 5. The compounds have suitable size and moderate number of rotatable bonds, suggesting a good potential for cell permeability. While showing moderate water solubility, the compounds adhere to other drug likeness filters, suggesting favorable pharmacokinetic properties in overall. However, we should take into account that HBMM has a slightly higher topological polar surface area compared to the other two compounds. These might indicate that potential decrease in cell permeability. Overall, the physicochemical analysis reinforces the potential of these shift-based derivatives as drug-based on their properties influencing ADME and drug-like characteristics. To conclude, let's make a quick recap. The study successfully synthesized and characterized 3 new shift-based derivatives using a combination of experimental and computational techniques. Techniques like infrared proton NMR and UV visible spectroscopy provided structural elucidations, while quantum chemical properties confirmed the structures further. Detailed analysis of vibrational assignments with potential energy distribution ensured accuracy. We investigated the potential antioxidant activity of the derivatives by calculating key thermodynamic parameters under various solvent conditions. The findings suggest that dependence on the surrounding environment with the split mechanism favored in polar media and hydrogen atom transfer mechanism more likely in the gas phase. Among the derivatives, HBMC emerged as the most promising candidate for radical scavenging based on its consistently lower BDE, IP, and ETE values. Molecular docking simulations explored the therapeutic potential of these derivatives as inhibitors of the ubiquinol cytochrome C reductase binding protein. All 3 compounds demonstrated favorable binding interactions within the protein active site, with HBMM exhibiting the strongest binding affinity. The specific residues involved in hydrogen bonding, p-stacking, and hydrophobic interactions provide valuable insight into the potential binding mechanism. Theoretical ADME-tox profiling revealed promising drug-like characteristics for all 3 derivatives. Notably, they adhere to the established criteria like Lipinski's rule of 5 and other filters, indicating favorable absorption, bioavailability, and potential for effective interactions with target binding sites. Key physicochemical properties like log-P and TPSA and rotable bond count further supported these findings. For future directions, the study highlights several exciting avenues for further research. In vitro and in vivo assays. In vitro and in vivo assays are crucial to validate the predicted antioxidant activity and the protein inhibition, establishing a strong foundation for preclinical studies. Targeted experiments to elucidate the dominant radical scavenging mechanism in different environments would complete the theoretical prediction. In-depth toxicity assessment of the most promising leads are paramount for their development as pharmaceuticals or safe food additives. Thank you for your attention.